Okay, so I just make a very quick introduction. Thank you, Razia, for joining us to present your work today. It seems everybody here knows Razia, well, more or less, but just to make a quick introduction, Razia is doing her PhD at the Department of Computer Science at Johns Hopkins University with Ilya. Her research interests are intersection of causal inference, missing data, algorithmic fairness, mediation analysis, and semi-parametric statistics. She has mentioned to me as well before that the main tool for her analysis are graphical models and semi-parametric statistics. And the assumption was that most of us here are quite familiar with these tools. She's happy to talk about her research today and present the results of her recent paper. And perhaps if there is any question from other papers, hopefully she would be able to help us with them. And yeah, I leave it to you, Razia. Thank you.
Yeah, thank you so much. Thanks everyone for tuning in. Let me just share my screen. Can you guys see? Is that good? Awesome. Yeah, it's a great pleasure to be here. Thanks for organizing and thanks for inviting me. It's a joint work between my colleague Rohit Bhattacharya, who is an equal contributor, and our advisor Ilya. So it's going to appear at the ICML soon this year, and please feel free to also interrupt me and ask questions if you have any during the talk. So before I jump into missing data, I just wanted to have a quick plug about the our recent Python package called Ananke Causal. Ananke is named after the Greek goddess of necessity and causality. It uses language of graphical models to do some cool stuff like identification of causal effects on the presence of unmeasured confounders, and do some semi-parametric inference for the targets that are non-parametrically identified, and do some other stuff like including the missing data identification that I'm going to talk about, and other things like surrogate experiments and stuff like that. And here are a few links that you can find more information on the package, and the main contributors are really Rohit Bhattacharya and Jaron Lee in our lab. Here's a quick screenshot of what it can do. So you can just plot your model in the language of graphical models, whatever that you like, whether it's a DAG or whether it's an ADMG with bidirected graphs that accounts for unmeasured confounders and stuff like that. And you can specify a treatment and an outcome, and it tells you whether that effect is non-parametrically identified or not. And if it is, it's going to give you a list of estimators on how to actually estimate it, and among them leaves semi-parametric and double robust and efficient estimators. And it's going to you pick the estimator, and it's going to calculate the effect and gives you some confidence intervals and stuff like that. So if you get to interact with it, we would love to hear your feedbacks. Awesome. So back to missing data. So we have some data with NID and IID samples, and there are some, we want to perform a task, whether it's a prediction, whether it's a causal analysis, but there are sometimes missing entries because of various reasons. There could be dropouts, there could be loss to follow-up, censoring, and stuff like that. So what should we do in order to correctly estimate the target of inference had there been no missingness? Should we try to use complete cases? Should we impute? But this this phrase of "had there been no missingness" is kind of like reminiscence of how we think in causal inference in the language of counterfactuals. And one way that people get around the fact that we can't really observe multiple counterfactuals for each individual in order to find the average causal effect, they try to reweigh their data by the propensity score, which is the probability of the treatment given the outcome, and calculate their effect. So maybe a more reasonable thing to do here is to just reweigh complete cases also by the probability of missingness. But the question is, what is this? What is an appropriate strategy to actually find these probabilities and estimate them? So the objective in our missing data research is doing non-parametric identification of quantities had there been no missingness as functions of observed data, and then do estimation on top of that. So this talk is mostly focused on the identification part. And as we know, identification always comes with assumptions, but that's fine. We can argue what assumptions are better or not. We want assumptions that are easily interpretable, they are conveyable, and they are really reusable regardless of what query we are interested in, whether it's like a simple mean we want to calculate, whether it's a causal effect or something else. But before we talk about assumptions, we want to know what missing data models are. So there are really sets of distributions over two types of variables that are always observed, that are denoted by O, and a tuple over that are associated with variables that are missing, that are sometimes missing. So what is in the tuple? There is x parentheses 1, which denote the set of variables that are potentially missing. And we want to distinguish them with what we actually observe by putting this superscript parentheses 1, like we call them counterfactuals also. And there are also these missingness indicators that corresponds to the missingness indicator of variables in this set of counterfactuals. And r equals to 1 denotes that the random variable is actually missing. And there is this third variable called the proxy of the counterfactual that is deterministically defined and is denoted by x. So this I really indexes the variables in the set. So for each proxy variable, how is it defined is that we look at the missingness indicator, and if it's 0, the proxy is going to be a question mark in the data, and if it's when the missingness indicator is 1, the proxy is going to be equal to the counterfactual. It's really like similar to the consistency assumption that we have in causal inference. And how we would factorize the joint distribution is really a factor over three terms. The first term is the probability of the observed variables and the counterfactuals, that we call them the target law, times the probability of the missingness indicators given these observed variables and the counterfactuals, as some people call them missingness mechanism, because they are really the ones that tell us how the missingness actually happened, why variables are missing, times something that is kind of like boring term, this really the proxies given the missingness indicators and the counterfactuals, and why they are boring, because they are clearly deterministically defined. And we call the product of the target law times the missingness mechanism as the full law. And what we really observe in practice is a coarsened version of the full law, where we don't really see the counterfactuals, we only see a coarsened version of them, or proxy of them. So what we have is really P of distribution over the observed variables, the indicators, and the proxies. And what we mean by identification is that we say a quantity is identified if it can be expressed as a function of observed data. And if we have the full law, if we can identify the full law, then really we can perform any inferential task that is concerned with the full law. And it's kind of like aligns with our reusability condition also that I just mentioned. So it's a good target really to look at for for the purpose of identification. And by simple Bayes rule, we can show that really in order to identify the full law, we only need to identify the missingness mechanism. Why is that? Because based on the previous slide, I said that we know that the full law is equal to the product of the target law times the missingness mechanism. And we can write down the target law as like this division where we have the full law divided by the missingness indicator, where the missingness indicators are evaluated at 1. So the numerator, by consistency, we can just replace the counterfactual with the proxy. So the numerator is identified, and the denominator, if we have the missingness mechanism, so we have the denominator as well. So that's why we say the full law is identified if and only if the missingness mechanism is identified. So we kind of like shift our focus to now identifying the missingness mechanism. And again, we need assumptions in order to identify this missingness mechanism. And the assumptions can be really hard, sometimes too technical to communicate, especially in collaborations with folks that are in our group, but they are like from different disciplines. For interpretability purposes, we just turn into graphs, and the simple form of graphs is DAGs, which have directed edges with no directed cycles. So the missing data DAGs also is similar in concept to DAGs, but the slight modification because we have to account for these deterministic relations also between these counterfactuals, proxies, and the missingness indicators. And on top of that, we also don't want to allow some directed edges. So let's talk about some conventions, what is allowed and what's not. So we have our tuple, the counterfactual, the missingness indicator, and the proxies here. And the proxies, as we said, they're deterministically defined, so they have only the missingness indicator and the counterfactual as parent. And we show these edges in gray to just like distinguish them from other types of edges. So what it means is that each proxy, they can't really have other counterfactuals or other missingness indicators pointing to them. So it's deterministically defined and they have only two parents. And we are not allowing for directed edges from the missingness indicator to the counterfactual. This is really the other way around. So an example of a common and very popular missing data model is the missing at random or MAR. How do we represent it with DAGs? Is that the parents of the missingness indicators are always the observed variables, that are the variables that are fully observed all the time. And when the missingness indicator starts having counterfactual parents, then this is an example of missing not at random, really, or MNOR for sure. So how do we factorize the joint distributions of these MNOR models? It's really similar to how we factorize it in DAGs. It's a product over conditional densities of each variable given their parents. And again, we kind of like separate out these boring parts of the deterministic parts also from the factorization. And it's cool because familiar concepts like d-separation and Markov properties just carry over just fine. So what are examples of identified and not identified MNOR models? So here is an example of what's known as block parallel model with two variables in the literature. So this is the set of conditional independencies that these models contain are in this form, that each missingness indicator is independent of other missingness indicators and its corresponding counterfactual given their parents. All right. So we want to try to identify the full law here, and we said the full law is identified if and only if the missingness mechanism is identified. So we just try to play with this missingness mechanism, and we just like factorize it as the probability of R1 given its parents and probability of R2 given its parents. And we sometimes call these propensities, similar to causal inference, so propensity of R1 and propensity of R2. So the claim is that if these propensities are identified, then the product is going to be identified as well. So it's very simple to show why these pieces are identified in the block parallel model by simple rules of d-separation. So let's look at propensity of R1. The parents of R1 is just x21, and we know that R1 is going to be independent of R2 given x21. So I can just plug in R2 equals to 1, pass the conditioning bar, and then because R2 is set to 1, then I can replace the counterfactual with the proxy, and now the right-hand side is just a function of observed data. So therefore, the propensity of R1 is identified. Similarly, propensity of R2 is going to be identified. Therefore, the missingness mechanism is identified, and therefore, this is an example of MNOR model where the full law is identified. What's an example that is the full law is not identified? The simple one is called the self-censoring model. Well, the counterfactual is actually pointing to its own missingness indicator. And this is what it means, is that the full law, which is simply just P of x1 here, is provably not identified. What do I mean by that is that I can come up with two full law distributions that agree on the observed law, but they are two different distributions really. So they disagree on the full law but agree on the observed law. It's similar to how we prove non-identification really in causal inference on the presence of unmeasured confounder. So clearly, some MNOR models are identified and some are not. So what we are after is really coming up with a graphical characterization of when and how MNOR models are identified. And for this characterization, we require two properties, soundness and completeness. What soundness means is that when we provide an identifying functional, this identifying functional is going to be the correct identifying functional. And by completeness, what it means is that if we fail to identify an MNOR model, then the MNOR model is provably not identified. And what that means is that no other algorithm can actually identify this MNOR model without making any extra assumption. All right. So missing data identification has been around for more than a decade now, but really no completeness result has been found really, and with this paper we provide really the first completeness result on missing data identification for full law. So I'm gonna start talking about an example that actually broke the literature in why other algorithms actually fail to identify some MNR models, and how we are gonna identify it using this the odds ratio parameterization. So I'm just gonna pause for a second, see if there are any questions.
Yeah, so when you say you're looking at a case where you're identifying the full law, of course, there's already a solution for any question you want, but of course it's conservative, right? That you may have particular functionals that you want to target. Or
right, yeah.
do you have examples of that? Things that you could identify with by targeting to a particular functional, but not, the full law is not identifiable?
Yeah, exactly. So that's so there are when full law is identified, means that any function of the full law is identified, means that the target is going to be identified, but it's nearly not the other way around, because target law is for target to be identified, we only require the missingness mechanism to be identified when all the missingness indicators are equal to 1. So we don't really require all the we don't require the missingness mechanism to be identified when r equals to 0, for example. So that's require really like a that still, though, coming up with a complete algorithm for target law is not, there is no complete algorithm to come up with target law identification. So yeah, it is correct that if you try to look at like finer set of targets, then yeah, they may still be identified, but really the focus here was to identify the full law. And if we have that, we have everything. Okay. Awesome.
I have other question too. Sorry. So when you forbid the errors from R to X1, of course, I can see the reason for that. But of course, you can think of stories where by saying that they're going to measure something, you change what they're going to be measured. For example, like in psychology, when you say, I'm going to ask this question to you, instead of trying to infer a question directly. Of course, this looks a bit contrived. I just try to see whether there is already understanding the cases where the error, whether you're missing something by forbidding edges from R to X1.
Yeah, there could probably be cases, but really we can just think of causal inference also like to see whether it's really a reasonable assumption or not. Like in causal inference, if we try to include the counterfactuals on the graph, so the counterfactual is going to be correlated, but really they are not a function of the treatment. So it's just the final proxy that is a function of the treatment and the counterfactuals. So it's not that the treatment is pointing to the counterfactuals. It's really, yeah, it's.
But as well, when I was thinking about general terms, they're not necessarily counterfactuals. But in psychology, as I said, even in social science, you have questionnaires where the order by which you put the questions may affect your responsiveness. So answering earlier questions might make you get high and not answer later questions.
Yeah, that is true. So, but we are allowing for edges from proxies, for example, to the R, not from the counterfactuals to the R. Right. So there still could be proxies pointing to the other R's. But what we are excluding is other R's pointing to the proxy, because the proxy is deterministically defined, given its own indicator and the corresponding counterfactual. Okay. Cool. If there are no questions, I'll move on. So here's an example, and we ask the question whether the full law is identified or not, and we try to look at the missingness mechanism and factorize it by looking at the propensity of R1 given parents, R2 given parents, and R3. And we say that if each missingness, if each factor is identified really, then the product is going to be identified. So it's easy to see why the propensity of R1 is identified, again, by the separation. Parents of R1 is R2 and X31, and given R2 is going to be independent of R3. So I can just plug in R3 equals to 1, pass the conditioning bar, and by consistency, again, I can replace the counterfactual with the proxy. But really, I can't do the same thing with propensity of R2. So because R2 has R3 and X11 as a parent, but I can't plug in R1 equals to 1. because it's a direct child and it's not really not independent of it. So this simple d-separation check is gonna fail. And similarly for R3 also, I'm gonna fail to identify it that way. But like in our previous result and in the literature, what we say is that okay, it may not be identified in this tag that I'm looking, but it may be identified in a post-interventional distribution where I try to fix some stuff or intervene on some of the missingness indicators, and then the propensity is going to be identified maybe in that in the conditional tag that I get. So the idea is that because R1 was identified, I'm just going to intervene on R1. And what it means graphically is that I'm just going to get rid of all the incoming edge to R1. And then probabilistically, what it means is that I'm just dividing the joint by the propensity of R1. It's really how we do that in causal inference. When we are intervening on the treatment, we just divide by the probability of treatment given parents. All right. And then one important thing to notice here is that in this CDAC, I'm gonna have we are selecting on this R3 because in order to identify the propensity of R1 in the process, we were forcing R3 to be 1. So that's why, like in this intervention, in interventional distribution, this R3 is now selected on and it's being 1. So what it means is that if I try to identify propensity of R2 in this graph, what I'm gonna get is only the propensity of R2 when R3 is equals to 1. So I'm not gonna, with this simple trick of intervening on R1, I'm not gonna identify the propensity of R2 at all levels of R3. And again, because R3 is now selected on, I can't do really other interventions. I can intervene on R2, and I'm gonna fail in identifying propensity of R3 altogether. So now, does it mean that the missingness mechanism is not identified, and does it mean that the full law is not identified? Well, let's see. So we said, just to summarize, we said the propensity of R1 is identified. Propensity of R2 is identified only when R3 equals to 1, and we fail to identify propensity of R3. So, but the key observation here is that if I include R2 past the conditioning bar in the propensity of R3, then that distribution, which is probability of R3 given R2 and X11, is suddenly going to be identified. Why that is why this is a quick scratch note. We see that R3 is going to be independent of R1 given R2 and X11. So therefore, I can just plug in R1 equals to 1. And then again, by consistency, I can see that the right-hand side is a function of observed data. And there we have it, the propensity of, it's not really propensity. So the probability of R3 given R2 and X11 is now identified. So what does that mean? Can we identify now the missingness mechanism using this new information, these new identified pieces that we have? So the game plan here is now to use the conditional densities that we identified and get the identification of the missingness mechanism. So let's look at the factorization of the missingness mechanism slightly in a different way. So let's write it down as the probability of R1 given parents times the joint distribution of R2 and R3 given their parents, which is just X11 here, okay? So that would have been awesome if we could write down this joint distribution as these two conditional distributions that we identified times some leftovers that are just kind of like easy to show that it's identified, right? But it turned out there is such a formalization. It's called the odds ratio parameterization that was introduced in 2007 by Yoon Chan. Here's what it says. It says that given disjoint sets of variables A, B, and C, and reference levels A0 and B0, we can write down the joint distribution of A and B given C as a product over conditional distribution of A given that B is evaluated at its reference level and C times probability of B given that A is evaluated at its reference level and C times the odds ratio of A and B given C. So here, the Z term is really the normalizing term, which is sum of the numerator over all possible values of A and B. And the odds ratio of A and B given C is defined as the odds of A given B times the inverse of odds of A given that B is evaluated at the reference level and C. All right. So here's kind of like you can see, but that why this what we wanted to do is kind of this parameterization may help, because you can think of R2 now as A, R3 as B, and X11 as C. And this stuff that I wrote down in red is kind of will look like the odds ratio term. Okay. So maybe this parameterization is might be new to some people, especially this odds ratio term. So let's look at some of its characteristics. So odds ratio is symmetric. What it means is that in order to define what the odds ratio is, besides using the odds of A, I can use the odds of B in order to define the odds ratio. So I can use the distribution of B given A and C in order to write down what the odds ratio is. And it's easy to see that the odds ratio also is going to be evaluated at 1 whenever either A or B are evaluated at reference level, because of the cancellations that really happens in these cases. So the only interesting part, the only interesting evaluation of the odds ratio happens when neither A nor B are evaluated at a reference level. So what is a good reference level in our missing data case is when R is equals to 1, because then I can use consistency, for example, in order to argue about the identification later. So this kind of like gives us a new way of thinking about identification. So previously, in order to identify the missingness mechanism, we said that we need to identify every single propensity score, and then therefore the product is going to be identified. But now with this new parameterization, we have to identify a slightly different sets of models. Specifically, what we need to identify is different conditional distribution, which look like this, where R's are evaluated at 1 past the conditioning bar, and the odds ratio term where R's are evaluated at 0, because otherwise the odds ratio is going to be 1, and that's not interesting. So with this new information, let's go back to the previous example and see if the joint distribution of R2 and R3 given their parents is identified or not. Is there any question?
This is a bit beside the point, but do they need, for the original result on the odds ratio parameterization, does the distribution need to be discrete, or any density function also have that finite Z?
As far as I know, there is no restriction on the distribution. Okay. So if I want to use the odds ratio parameterization to write down the joint distribution of R2 and R3 given X11, this is how it looks like. And based on our previous discussion, we know that these two terms, these two conditionals are identified. We only need to show that this odds ratio term is identified or not. We write down, we expand the definition when R2 and R3 are equals to 0 using the conditional distributions of R3 given R2 and X11. And because we showed that R3 given R2 and X11 is everywhere identified, then this odds ratio is going to be identified. Why? Because like all the terms are really R3 given R2 and X11, right? But like evaluated at different levels, and because this conditional is identified everywhere, then the odds ratio is going to be identified. So what that means is that now the joint distribution of R2 and R3 is identified. What that means is that now the missingness mechanism is identified. And what that means is that the full law is identified. And once we have the full law, we have any function of the full law is now going to be identified. And really with this, so we show that an MNOR model in the literature that was known to be not identified is now identified using a different trick. Okay. So let's do another example. So this is exactly, this DAG is exactly the same as the previous scenario, except for this added edge from X21 to R3. So because it contains the previous example, in other words, it's a supermodel of the previous one, it's gonna applying all the algorithms in the literature is gonna fail again on identifying the full law here. But let's see if it is identified using this new trick that we learned. So again, the missingness mechanism is the propensity of R1 times the joint distribution of R2 and R3 given the parents, which is now X11 and X21, right? So the problematic part again is this joint distribution, because propensity of R1 is just easily identified by the separation. So here's the expansion on how we write down the joint distribution in terms of the odds ratio. And for this to be identified, we need to identify 3 pieces. So P of the distributions of R2 given R3 equals to 1, X11, and X21 is identified by this separation, because we can just drop X21 here. And then R3 here, condition on R2, X11, and X21 is gonna be only identified when R2 now is 1. Why that is? Because now R3 has X21 as a parent. So therefore, R2 has to be 1, so that I can use kind of like consistency and say that, yeah, okay, so this is now a functional observed data. And so this is what how it differs from the previous example, really. And because of this fact that R3 is now the conditional distribution of R3 given R2 and the parents are not identified everywhere, it's not very easy to see why the odds ratio is going to be identified. So let's take a closer look at the odds ratio. And we say that odds ratio is symmetric, right? So there are 2 ways of writing it down. So let's focus on the left-hand side. On the left-hand side, we are using the odds of R2. So by this separation, we can see in this graph that R2 is independent of its corresponding counterfactual X21 given R3 and X11. So what it means that I can just drop X21 past the conditioning bar. So what it means is that now I can go back to the odds ratio formulation and drop X21 from all the terms. So what it means is that now the right-hand side is not going to be a function of X21 anymore. So therefore, the left-hand side, the odds ratio, should not be a function of X21. So I'm just like summarize this information by just writing down the odds ratio is now only a function of R2, R3, and X11. So similarly, I can play with the odds of R3 now. I can say that R3 is independent of R1 given R2, X11, and X21. So now I can just plug in R1 equals to 1 past the conditioning bar, and then I can replace X11 really with this R1 equals to 1 and the proxy X1. So what that means is I can go back to the odds ratio formulation and do the same thing for whenever I see X11, I can replace it with R1 equals to 1 and X1. So what it means that now the left-hand side should be just a function of R1 equals to 1 and X1. So I'll just summarize this information by just saying that now the odds ratio is equals to, is just a function of R2, R3, R1 equals to 1, X1, and X21. So because the odds ratios are symmetric, they are equal, what it means that now these 2 functions, F1 and F2, should be equal. What it means that now the odds ratio should be only a function of the intersection of the stuff that are in the arguments of these functions. So it means that odds ratio should be only a function of R2, R3, and R1 equals to 1 and X1. And you can see the right-hand side now is just a function of observed data. So therefore now the odds ratio is identified by a slightly different argument, which is this is symmetric argument of the odds ratio. And then what it means is that now, again, the missingness mechanism, and as a result, the full law is going to be identified. Okay, is there any question?
I find this construction very interesting. Is this type of argument using other contexts? I mean, is this, I never seen people exploit the odds ratio that way, placing in right. Such a arrangement, identifying the scope of the function. Is this a type of technique is used elsewhere too?
I assume so, but like it's pretty cool, yeah, that there are different representations of the odds ratio and how you can actually exploit that and argue for identification. For the estimation part, is slightly different, but how you actually go ahead and estimate it. But then from the identification point of view, it's just pretty decent.
Yeah, it's very interesting how sometimes you try to show that the scope of some factors is not what intuition might tell you.
Right. I mean, it may help us really down the road for identifying target law as well, but really we haven't explored that avenue yet fully. And so now an intuitive question to ask is that why can't we just like use odds ratio parameterization on the entire missingness mechanism, right? And the answer is, yeah, we can do that. And here's how it looks like. It's really a product over these conditional distributions of each missingness indicator, given that the rest of the missingness indicators are evaluated at 1 times, and all the counterfactuals, times these odds ratio terms. It's kind of like a bit of mouthful, but what we really want to get is that in order now to identify the entire missingness mechanism, what we need to identify is two sets of models, these conditional distributions and these odds ratio terms. And now the question is, when do we succeed and when do we fail? So in our previous results, we say that we introduced this non-identified structure called the cluder. We said that if there exists two missingness indicators, Ri and Rj, such that Rj has both Ri and the corresponding counterfactual Xi1 as parent, then the propensity of Rj is not going to be identified when we evaluate Ri as 0. So here's an example with two variables. So R2 now satisfies this condition because R2 has R1 and X11 as parent. And what it means now, R2, this structure we call a cluder. So R2 is involved in a cluder structure now. And what this result is saying is that the propensity of R2, given that R1 is equal to 0 and X11, is not identified. And just to be more concrete, let's assume we have binary data. So therefore, the full law here is has 7 parameters, and out of which 5 are easily to show that are identified by simple rule of d-separation. I'm not going to go over them to save some time. But then the 2 remaining parameters are not identified, and those correspond to whether x11 is 0 or 1 in case of binary, right? So what do we mean by saying that these parameters are not identified? So how do we prove them really? So here's some probability tables. Each denotes the conditional distribution of each variable given their parents. R1, X11, and X21 don't have any parents, so there are 3 parameters here. And then R2 has two parents, R1 and X11. It has 4 parameters, and the red ones are the ones that are not identified. So how do we show that they are not identified? We should come up with 2 examples where they disagree on the full law, but they agree on the observed law. And we can easily show that we can say that there are actually infinitely many such examples if we compare the probability tables of the full law and observed law side by side. And we can see that, yeah, there are infinitely many examples as long as a weighted sum of these unidentified parameters stay the same across the examples that we have. And we can easily think of infinitely many such cases. So this is what it means that it's not identified. So in our previous results, we realized that self-censoring edges and cluder structures are problematic structures in the sense that they're going to mess up the identification for us. But what we really didn't know was what other structure are actually like problematic and what other structure screw up the identification for us. In other words, we didn't have really a complete characterization of identification of DAGs. Missing data DAGs. So in this paper, we show that actually the self-censoring edges and cluders are the only structures that are problematic for identification of full law. In other words, full law, that is a markup relative to a missing data DAG, is identified if and only if there is no self-censoring edge and there is no cluder. So this result is sound, and we prove that this result is sound and complete. And what are the identification functionals are given by the odds ratio parameterization. I'm going to go over the proof sketch very quick because I think it's very cute. So just the absence of self-censoring edges and cluders. So what they imply are these set of assumptions that each missingness indicator is independent of its corresponding counterfactual given the rest of the graph. So so this was really the odds ratio parameterization of the entire missingness mechanism, and we needed to identify 2 pieces, these conditional pieces of each missingness indicators given that the rest of indicators are 1 and the counterfactuals. And it's very easy to see why they are identified because because of these conditional independence, I can just drop the corresponding counterfactual parent, and then because everything else is evaluated at 1, then I can just use consistency to replace these counterfactuals with the proxies. And therefore, these pieces are all identified very easy. The problematic, the more subtle parts are really these odds ratio terms. But in order to argue for that, again, we use like a symmetric argument by showing that these odds ratio terms of Ri and Rj given the rest of the graph is not a function of the corresponding counterfactual parents, which are Xi1 and Xj1. by running really a similar argument that I just described in that example. And therefore, these odds ratio terms are going to be identified, and that really that's it. And we also showed it's also easy to see that these DAGs that are lacking self-censoring edges and clusters are submodels of what's known as item-wise conditionally independent non-response model that was introduced by Mauricio Sadinley, and no self-censoring model that was introduced by Ilya. And it was further studied by Dan Malinsky and Eric Shevchenko and Ilya. Okay, so this is really the completeness result for DAGs. Just to show how easy to check these results are, and we have this example, for example, and we want to know what is the whether the full law is identified or not. You can just immediately check if there is self-censoring edges or occluders. So there is no self-censoring edges because there is no counterfactual pointing to its indicator, and there is no includer. For example, R1 has X31 as a parent, but it doesn't have R3 as a parent. So, and similarly for R2 and R3. So therefore, full law is identified, and that's it. But a nice thing about this graph is also that if we start kind of altering edges by orienting them the other way or adding extra edges, they're gonna introduce either self-censoring edges or occluders. So those graphs are not gonna be, their full law are not gonna be identified in those DAGs. All right. So, so that was the results for DAGs, but we know DAGs are cool, but they're nearly not very realistic because we have unmeasured confounders. And it's not that sometimes variables are not simply missing, but completely unobserved. So what should we do then? So that's fine. And we can start putting unmeasured confounders on top of the DAG. Let's say here, for example, we may believe that there is an unmeasured confounder between X11 and X31. Maybe X11 is the smoking status, X31 is the bronchitis test, and the U1 may be some genetic trait, for example, that may cause both of them, and we haven't measured that. Or maybe there are also unmeasured confounders between X21 and the missingness indicator R3. X21 could be some measurement in lung, for example, the TAR in lung, and R3 is missingness of the bronchitis test, and we may think that okay, maybe the individual's occupation, for example, may be something that affects the two, and because they are closer to factory, for example, and then they have more tar, for example, in their lungs, or and the fact that they are closer to factory, they get tested more, for example, for bronchitis and stuff like that. So, but it's similar to causal inference, working with DAGs with hidden variables are kind of like hard not that hard, it's just like there are easier ways to think about identification when we have DAGs with hidden variables, which is just what's known as the acyclic directed mix graph, which is a summary of the DAGs with hidden variables where we project out these unmeasured confounders. There is some projection rules on how we actually do that, and you guys probably know, but it's just like suffices to say that whenever we see bidirected edges on the graph, they're going to correspond to an unmeasured confounder that points to the variables on the endpoint. Okay. So now the ADMGs are kind of like more complicated models because factorization is more complicated, and but the nice thing is that the results concepts like d-separation generalizes to what's known as the M separation, and they're nice. The M separation generalizes the definition of collider to include these bidirected arrowheads. So again, so let's talk about identification again. So we have this graph, and we want to know whether full law is identified or not under these unmeasured confounders that we have. So one easy check is to see if the previous assumptions that we have for DAGs are they are satisfied here or not. And by M separation, or really by looking at d-separation on the DAGs with hidden variables, where you replace these bidirected edges with the unmeasured confounders, we can see that each missingness indicator is actually independent of its corresponding counterfactual, given the rest of the graph. So all these assumptions are satisfied in this case for us. So therefore, we can just easily rely on the previous result and say that, yeah, okay, the full law is now identified. All right. So what if we start, so we are allowing for unmeasured confounders among the counterfactuals, between the counterfactuals and missingness indicator, and between the missingness indicators. So now what happens if I add these unmeasured confounders between the missingness indicators? So there suddenly all these assumptions are gonna fail because they're gonna open up some colliding paths, right? But we knew that the full law is not really identified in this graph by other means. So then what does it mean? Here, the interesting thing is that there is no self-censoring edges and there is no clue there as well. All right, but what is this like mysterious new graphical characterization that gonna disable us to identify the target, the full law here? So we introduced this new structure called the colluding path. We said that there exists a colluding path between the pair missingness indicator and the corresponding counterfactual xi1 if the two are connected through at least one colliding path. So a colliding path is a path where every vertex on the path except the two endpoints are a collider. So you can think of really colluders as a special type of colliders. So these are all possible colluding paths between the missingness indicator and the corresponding counterfactual. And each pair of these dashed edges means that either in presence of either one or both, we are still gonna have a colluding path between the two, between the pair. So, and then we showed that full law, that is markup relative to the missing data acyclic misgraph, is identified if and only if the graph does not contain any colluding path. And it turned out that this result is again sound and complete, and the identification function is given by the odds ratio parameterization. And the proof sketch is really similar to what we had in DAGs by noting that the colluding path really imply the same set of assumptions, that each missingness indicator is independent of the corresponding counterfactual given the rest of the graph. And so we provided, again, counter examples for these unidentified structures that I just mentioned using Mobius parameterizations of the ADMGs. So just to see how easy this result is to implement is that now I have this ADMG again, and I'm asking whether the full law is identified or not. So I should look for colluding path, and I can see one colluding path is really between R1 and X11. Is R1 bidirected path to R3, and then X11 pointing to R3. So there is a colluding path between the two. And as soon as I see this one colluding path, I can conclude that the full law is really not identified. But there are more colluding paths that you can find. There actually turned out there is colluding paths between all the pairs, between R1X11, R2X21, and R3X31. So yeah, the full law is definitely not identified. So really that brings me to the end of the talk. Just some quick conclusion. We provide a sound and complete algorithm for full law identification and in either presence or absence of unmeasured confounders. And we have this odds ratio parameterization when the full law is identified. And as Ricardo pointed out, if the full law is really identified, all functions of full law are identified, including the target law. But really it's nearly not the other way around, that if full law is, we have, for example, some DAGs that have colluders, or we have some ADMGs that have colluding path, there might still be a chance that the target going to be identified. In fact, we discuss some ways of how these things are actually identified, even in presence of these problematic structures for full law, the target is still going to be identified. But unfortunately, there is still no complete algorithm of how to characterize the identification of target law even in DAGs without the unmeasured confounders. And thank you very much.
All right, thank you.
Yeah.
That's quite a combination of many different pieces. I haven't seen people using proofs elsewhere. So that's quite, I don't know, includes myself. So that's quite impressive to have all these novel ideas put together for this problem.
Yeah, we were very bothered by this lack of completeness results, because it was, I mean, we were just kind of restricting ourselves by thinking that, for the missingness mechanism to be identified, all the conditional pieces or the propensity should be identified. But as soon as we start diverging from that mindset, and it kind of like helped to find new ways of identification. And it turned out that you can get identification in just one shot. You know, like you can apply the odds ratio on the missingness mechanism entirely. I'm just gonna stop sharing, and if there are,
What could I ask what made you suspect that the odds ratio parameterization would help you with identifiability?
would help with identifiability of what
Of the full law. So you like, did you just sort of stumble upon the odds ratio parameterization, or you sort of like was there some intuition behind why you started looking at this?
we definitely knew about odds ratio parameterization in our lab,
Yeah,
because people in our lab work on odds ratio parameterization. So like Dan was working with Eric and Ilya on coming up with semi-parametric estimators for the no self-censoring model that I mentioned that Ilya and Sadinle introduced simultaneously. So we kind of knew, but like when we knew it even when we had like the UAI paper, but just linking it to this was didn't happen really.
Yeah. Another interesting avenue of future work that you talk about in the paper is about sort of estimation theory.
Yeah.
So yeah,
I can
how would
share
that?
my. That's actually a good question. I can share my screen again. I have like a spare slide on. So there are ways of actually like estimating odds ratio. And there are even like semi-parametric ways of doing it. I think there are like double robust estimators for it. But like here's a quick example of this block parallel model that I mentioned, and how actually we would estimate this odds ratio when R1 and R2 are evaluated at 0 is we consider these U thing. So it's just really the indicators of R1 and R2 divided by the propensity score, and times when the propensity score is actually evaluated at 0 minus these terms. And you can show that this expected value of U is equal to 0. And what it means is that if you solve this estimating equation, you're gonna get the odds ratio parameterization. Why? Because if you use the odds ratio parameterization for this term and this term, things gonna cancel out, and what you can get is just the odds ratio in one piece. And you have even like an explicit form of writing it down, so you can just change terms, moving terms around, and then odds ratio is gonna be equal to a specific thing. And yeah, so that people then build on top of this, and there are like other ways of estimating odds ratio.
Given that the odds are binary, how much efficiency do you get over maximum likelihood, for example?
I haven't, like me personally, haven't worked on estimating it and knowing how hard or easy is really. But we are trying to like use odds ratio parameterization to actually do model selection with this thing. And so because, the full law is identified, but we are assuming that the missingness mechanism is given as represented by the DAG. But then how do we actually go ahead and learn it ourselves? So that's.
Given, I think we tend to assume that missing data is not that big of a problem, but I think it might be a big problem in certain applications. So have you had a chance to apply it to some data sets? And was there anything that you learned from that? And maybe is that something you're trying to do with Microsoft as well in the internship right now?
No, Microsoft thing is totally different. It's about the interference and stuff. But we, before this ICML paper, we tried to write an estimation paper for this, for target identification. So we had a procedure on how to actually like identify some target laws, but we didn't have a complete algorithm. But it was nice in the sense that it would lead really to this nice inverse probability weighted approach that we could just like recursively apply it and then get the target. So we looked at some HIV data and did some simulations to actually see if we incorporate the true missingness mechanism, and if we just do reweigh the rows using this these estimates that we get can we break, for example, something like mice by just imputing things. And we got some interesting results, but we never get to really. We were more interested at the time to do completeness results for our sanity, but like yeah, that's something that we are thinking actively about.
Do you think there's a way to, I guess, so like missingness is sort of like a hard idea, but like, do you think there's a way to sort of connect this to like measurement error modeling, where like you don't have this sort of binary missingness, but you have some other bias that you might suspect
people lie in
is sort of
the
like,
answers, for example.
what's that saying?
People lying in answering a question, and you may have a model how they lie.
Yeah,
or even
something like
consistency,
that.
right? You may think you ask the same question twice to a person, and they might answer different, but that's a bit different. It's less systematic.
Yeah.
Right. I haven't personally worked on measurement error much, but I think so. Like, what the little knowledge that I have is just like people try to incorporate like proxies on the graph of whether this actually captures the truth or not, and they have like assumptions, and sometimes they do like they try to draw their assumptions also on graphs. But I think this result is just like saying as long as you have your assumptions drawn on some way on the graph, and if you are interested in some targets, is it going to be identified or not, regardless of whether you have proxies or whether how you define your variables and stuff like that.
Yeah, now that you mentioned related problem, Matt, the other problem is maybe as closest to this is selection bias, right? It's a typical case, a condition on condition the value of a variable may not be the target that you want.
Right. Yeah, exactly. I think one person in our lab actually like used this selection bias criteria that we have, like what is fixable in actually in missing data, and use it like in surrogate experiments. And actually like because they they have this selection bias problem also, and that's interesting.
Yeah. Because one thing we try to argue, I'm not sure this is correct, but in many cases, you could see the missing data as a special case of selection bias, except for some deterministic relationships, right? I mean, exploiting a lot is deterministic relationships anyway. That can think is an even harder problem. In the selection bias is more general, even harder problem.
Right. Yeah, probably. Like we thought for, I mean, I personally thought like sometimes the way causal inference was introduced to me that it's like a missing data problem. You have counterfactuals and some you have question marks in your tables. But I think it turned out that missing data is a harder problem than causal inference. Like in DAGs, for example, all causal effects are identified, but in DAGs of missing data, then not all effects are identified. Not all the targets are identified, right? And yeah.
Yeah, I guess if you wanted to sort of extend the selection bias, you'd have to have some, like you were saying, Ricardo, some idea of the function that was selected a bit, like.
I mean, not necessarily. There are ways of recovering from selection bias. There is, including a workshop paper by Robin Evans and Vanessa Dideles, where they, I think it's maybe just Vanessa. I don't remember whether it was Vanessa. And
I think it was Vanessa. So, yeah, I think I know what paper you're referring to.
Yeah, it was there are cases where, depending on your query, depending on the independent structure, you may reformulate your query so it doesn't matter that you are in a bias sample. You condition of particular outcomes.
Yeah. I see.
But I don't know what the latest, I don't know. I'm pretty sure that some of the ideas that Razia presented here are probably useful in generalizing what's up there. Selection bias. But it should be even harder. Yeah, there's a paper I had in mind. Well, it's Vanessa and Robin, yeah. All right, any further questions, people?
I do actually have a very practical question. When you, so I didn't go through the Chen 2007 with the odds ratio, but why is it that we choose the reference value to be 1? It says convenient, but it's not obvious to me.
It's why, sorry, you got cut. So you mean, why do we have the reference level to be 1 in our odds ratio parameter?
Yeah, and considering I don't actually know how this odds ratio thing works.
Yeah, I think it was just mainly because of the fact that we are doing missing data, and the way we like really denote the missingness. It's just like when it says it's 1, we observe what the proxy is, and when it's 0, it's question mark. If you change the notation, you can just like change your reference level as well. Yeah.
Yeah. Okay, that's what I thought. Cool. Thank you.
Yeah, I can figure out the odds ratio related to the 2-dimensional logistic regression problem. So suppose the outcome variable is two discrete variables instead of 1 discrete variable. And logistic regression is the log odds ratio, right, between 2 levels of a discrete variable. It's always in the baseline value. So if you have binary data, you only have 1 linear equation, right? Because the other is the baseline. So imagine you have 2 variables, then one of the combination of the 2 will be the baseline.
Yeah, I mean, the nice thing about this was because the missingness indicators are just binary, so that you can just like do the odds ratio on them also, but it really doesn't matter what the status space of the counterfactuals are.
Mm-hmm.
Yeah.
All right. Okay.
So is there any other question? Okay, thank you so much, Razia, for presenting today. It was very interesting work, and hope that I think I already can imagine that there are some ideas in people's mind, and hopefully it means collaboration in future. But thank you so much for your time, and thank you actually specifically because it's a holiday back in US, so we really appreciate it. And then please feel free to reach out to us if there is any, if you would like to have any follow-up or any further thoughts to share with us.
Yeah, thanks for having me. I enjoyed giving the talk, and it was a lovely discussion as well.
Thank you.
Thanks a lot for your time.
Thank you.
Yeah.
Thank you.
Thank you.
Yeah. See ya.
Ciao.
See you guys around. Bye-bye.
Bye.